Chapter 6: Quantum Mechanics and a Creation. The atoms or elementary particles themselves are not real. They form a world of potentialities or possibilities rather than one of things or facts. Werner Heisenberg. The quote just stated, "Capture the essence of quantum mechanics as a field that challenges our understanding of reality, inspires awe, and provokes deep reflection." My journey into the fascinating world of quantum mechanics began after watching a simple yet transformative video illustration of the Double Slit Experiment. That video was more than just an explanation. It was a spark that ignited a journey of discovery, profoundly shaping my view. The realization that, in the quantum realm, reality defies our everyday expectations was both enlightening and deeply inspiring. It opened the door to exploring questions about existence, reality, and even creation. Quantum mechanics doesn't just challenge our understanding, it redefines the very foundation of what we believe about reality. It introduces phenomena that seem paradoxical, such as particles existing in multiple states simultaneously, nonlocality where particles influence each other instantaneously regardless of distance, and the strange interplay between observation and reality. These phenomena are not mere curiosities. They strike at the heart of what we mean by existence itself. Among the many astonishing concepts I encountered, 3 stood out as particularly revolutionary in shaping my considerations about the nature of existence and the evidence of a creation event: the Double Slit Experiment, time dilation, and quantum entanglement. Each provides unique insight into the universe's inner workings, and collectively they suggest a cosmos of precision, interconnectedness, and intentional design. Quantum mechanics is an immense and intricate field, brimming with concepts that challenge intuition. Beyond these 3, numerous other ideas expand our understanding of reality. Quantum superposition shows that a particle can exist in multiple states or locations simultaneously until it is observed or measured. Superposition exemplifies the universe's fundamental indeterminacy at the microscopic scale. Quantum tunneling describes how particles can pass through energy barriers they classically shouldn't surmount, such as electrons tunneling through potential walls. This phenomenon underpins technologies from semiconductors to nuclear fusion in stars, showing that the quantum world operates beyond classical logic. The uncertainty principle, formulated by Werner Heisenberg, asserts that certain pairs of properties, like position and momentum, cannot be simultaneously measured with absolute precision. This isn't a limitation of our tools, but a fundamental property of nature. Quantum decoherence explains why quantum systems, when interacting with their environment, appear to transition into classical behavior, providing insight into how the macroscopic world emerges from quantum laws. The measurement problem arises because observing a quantum system collapses it from multiple possibilities into a single outcome. Yet why observation triggers collapse remains unresolved, a profound mystery of science. Nonlocality demonstrates that quantum correlations appear instantly across vast distances, defying classical constraints of space and causality. Quantum field theory, the most advanced quantum framework, combines quantum mechanics and special relativity, describing particles as excitations in underlying fields and offering a unified perspective of the microscopic world. Physicists also aim to reconcile quantum mechanics with general relativity, seeking a theory of everything through approaches such as string theory or loop quantum gravity, striving toward the unification of physics. With this context, we can now explore the 3 phenomena most relevant to understanding the universe's deep structure, beginning with the Double Slit Experiment. This is one of the most famous experiments in physics because it reveals how strange the microscopic world can be. It shows that tiny particles, such as electrons and photons, do not behave like ordinary objects. Instead, they can act like waves or like particles, depending on how the experiment is set up. Imagine a wall with 2 narrow slits and a screen behind it to record where particles land. If particles behaved like small, solid objects, we would expect them to pass through one slit or the other and form two simple bands on the screen, similar to throwing marbles through two openings. What actually happens is very different. When nothing is placed at the slits to track the particles' paths, an interference pattern appears on the screen. This pattern looks like overlapping ripples on water and shows that each particle spreads out like a wave and passes through both slits at once, interfering with itself. The pattern changes when a device is added to detect which slit each particle goes through. As soon as this path information is physically recorded, the interference pattern disappears. The particles now behave like individual objects, forming two broader bands on the screen. This change happens even if no person ever looks at the data. It is caused by the physical interaction between the particle and the measuring device, not by human awareness. Many popular explanations suggest that a human observer collapses the wave simply by watching the experiment. This is misleading. In physics, an observer does not mean a conscious mind. It means a measuring interaction. A camera, detector, or even the surrounding environment can destroy the interference pattern. The result is the same whether or not anyone is present to observe it. The experiment was first performed in 1801 by Thomas Young, who used light to demonstrate its wave nature. In the 20th century, scientists discovered that electrons also produce the same interference pattern, proving that wave-like behavior is a general feature of the quantum world. The experiment has since been repeated with many kinds of particles, always with the same result. The importance of the double slit experiment lies in what it tells us about nature. At the quantum level, outcomes depend on physical interactions, not on human perception. While physicists continue to debate how measurement should be interpreted, it reveals a universe governed by precise but unfamiliar rules, where measurement is a physical process that shapes what can be observed. Equally transformative is time dilation, a phenomenon from Einstein's theory of relativity that intersects intriguingly with quantum physics. Time dilation refers to the fact that time moves differently for observers in relative motion or within varying gravitational fields. There are two types of time dilation. Relative velocity time. Dilation occurs as an object approaches the speed of light, causing time to slow relative to a stationary observer. Gravitational time dilation occurs when time slows in stronger gravitational fields compared to weaker ones. Evidence of time dilation is abundant. The Hafele-Keating experiment of 1971 demonstrated that atomic clocks flown around Earth on commercial jets experienced time differently than stationary clocks, exactly as predicted. GPS technology also relies on corrections for both forms of time dilation to maintain accuracy. Without them, locations would drift by kilometers each day. High-speed particles in accelerators live longer than they would at rest, confirming relativistic predictions. Astronomical observations also show that light from stars near massive objects is red-shifted due to slower time in strong gravitational fields, matching theoretical predictions. Time dilation reveals that time is not absolute, but a relative dimension intertwined with space to form the spacetime continuum. It challenges our everyday sense of time as linear and universal, inviting us to rethink beginnings, endings, and the flow of existence. The block universe theory extends this idea. All moments, past, present, and future, exist simultaneously, and our perception of sequential time is an illusion. Einstein himself suggested that the distinction between past, present, and future is only a stubbornly persistent illusion. Some physicists even speculate that time might emerge from particle interactions rather than existing independently, suggesting a deeper layer of reality. Time dilation and relativity reveal a universe structured with immense precision and complexity, raising metaphysical questions about who or what designed this temporal framework and why. Could this be another hint toward a purposeful creation, providing a stage for conscious beings to experience, learn, and grow. This leads us to quantum entanglement, a phenomenon in which particles become inseparably linked, so that the state of one instantly determines the state of the other, no matter the distance between them. Imagine two entangled electrons sent to opposite ends of the galaxy. Measuring the spin of one immediately reveals the spin of the other. Einstein famously called this spooky action at a distance. Entanglement violates classical notions of locality and causality, suggesting an underlying unity to the universe. It has been repeatedly confirmed through experiments testing Bell's theorem, demonstrating that no classical mechanism can explain the observed correlations. The implications of entanglement are profound. Reality is fundamentally non-local, and connections can exist instantaneously. Precision in quantum laws is necessary for entanglement to occur, suggesting fine-tuning. The interconnectedness of entangled particles parallels ideas of a purposeful creation. Entanglement may metaphorically reflect a creator's connection to all aspects of creation, beyond the constraints of space and time. Together with the double slit experiment and time dilation, entanglement emphasizes the precision, interconnectedness, and depth of the universe, revealing a cosmos that is structured, responsive, and possibly intentional. Observation, time, and connection emerge not as arbitrary rules, but as fundamental aspects of a coherent, intricately structured system. Quantum mechanics compels us to reconsider what it truly means for something to exist, how time flows, and how the universe's elements are entwined in a vast, interdependent web. It invites us to step beyond the familiar, material view of reality and recognize that the cosmos is more than a backdrop for random events. It may be an exquisitely crafted stage upon which existence unfolds with deliberate intent. The double slit experiment, time dilation, and quantum entanglement reveal a universe of staggering sophistication where patterns emerge that are simultaneously precise and mysterious. Particles that behave as waves until observed, time that stretches and contracts according to motion and gravity, and entangled particles whose states are linked across immense distances. All these phenomena point toward an underlying order that is far from accidental. They suggest a universe that is deeply relational, where the observer and the observed are inseparable participants in the unfolding reality. The patterns of quantum behavior, the malleable rhythm of time, and the invisible threads of entanglement hint at a cosmos whose architecture is both intelligible and awe-inspiringly beautiful. These principles also illuminate the human experience in profound ways. We are not passive spectators in a disconnected universe. Rather, our consciousness, curiosity, and perception are woven into the very fabric of reality. The act of observing, questioning, and seeking knowledge is itself a form of participation, a reflection of the universe's relational nature. In recognizing this, we glimpse a profound resonance between human awareness and cosmic structure, where the act of discovery mirrors the universe's own elegance and intentionality. In witnessing the subtleties of quantum phenomena, the elasticity of time, and the mysterious bonds of entanglement, we encounter not only scientific truths, but profound philosophical implications. These discoveries call us to humility, reminding us that even as we probe the smallest particles and the vastest stretches of space-time, our understanding is always partial, our perspective finite. Yet within this limitation lies profound empowerment. The knowledge that we are capable of perceiving threads of order, glimpsing patterns, and intuiting the astonishing interconnectedness of all things. The universe, in this sense, becomes a mirror reflecting our own capacity to wonder, to comprehend, and to participate in its unfolding narrative. Contemplating the double slit experiment, time dilation, and quantum entanglement reveals a reality that is simultaneously fragile and resilient, chaotic and ordered, fleeting and eternal. These phenomena provide a window into the architecture of existence itself, showing a tapestry in which every particle, moment, and event appears interwoven with subtle precision. Observation, time, and entanglement are not isolated curiosities. They are signatures of a universe in which every element is meaningful and responsive. They hint at a cosmos where intelligence, order, and purpose may be inherent, and where the emergence of consciousness is woven into the very fabric of reality. The universe invites us to engage with it deeply, to marvel at its precision, to reflect on its beauty, and to recognize our place within it. In the subtle interplay of particles, the stretching and folding of time, and the invisible threads that link all matter, we discern a universe so remarkably orchestrated that it speaks to a mind behind its design, a creator whose presence is suggested not only through the laws that govern reality, but through the very act of our noticing, questioning, and awe. The cosmos, in all its complexity, interconnectedness, and elegance, becomes a living testament to possibility, meaning, and wonder, a silent, sublime invitation to explore, contemplate, and revere the astonishing unity of existence. In the elegance of quantum mechanics lies a profound question. Could this be mere accident? The universe's subtle symmetries, its breathtaking complexity, and the strange counterintuitive rules that govern reality certainly hint at something deeper, something beyond randomness. This is utterly profound,